Hello everybody, welcome to this webinar about advanced natural and mixed mode ventilation design. Let me see here, I think we are quite a few people now. Yep, okay, good. Okay, welcome to this webinar. We have been very excited about this. I just have some practical information to begin with. Hopefully everyone can hear me. And we have scheduled this webinar for around 60-minute time. And of course, if you have any question, you should be able to assign these in the questionnaire module to the right side where it says question, and in that you can address all the questions you have. All the questions going to the agenda, all the questions will be addressed at the very end of the presentation, so we will have a Q&A session. So here with me today is also Edward Dean, who is a principal at Bøheim plus Dean Inc. And he will explain you about the design and performance of natural ventilation system through different case studies of different, you can say, zero net energy buildings in California, and which lesson that he has learned from those ones. Furthermore, my name is Yannick Roth, and I am a Senior Building Performance Engineer at WindowMaster, and I will mainly focus on how these, you can say, problems can be avoided through some technologies that is available at the US market. Okay, so this is the agenda. So Edward Dean would start out with his presentation, followed by me, and at the very end we will have the Q&A session. You will still have the possibility to answer or to have your to give us questions along the presentations, and then we will handle these ones at the very end of it. Okay, but I will give the presentation forward to Ed, and then he will explain us what he has found out in these different case studies. Here you go, Ed. So that's brilliant. So you just have to, we can see your screen, Ed. You just have to unmute yourself, and then we should be, everything should be good.
Okay, so I think it finally responded to the microphone icon. So I presume everyone can hear me. I'm going to go through this at a good pace. I'm going to talk about case studies, particularly from the point of view of natural ventilation as a design strategy, as one of the design strategies. And wait a minute. Okay. And so I'm going to look at 3 buildings in particular in California that we looked at early. And I will explain each one and where natural ventilation fits in, very importantly, to each one. And maybe most importantly, what were the lessons learned? What these were basically prototype or early zero net energy buildings. And of course, when the first time through anything, you learn a lot of things to do better the next time. And there were lessons learned in these 3 buildings. Although they were all very successful, they were zero net energy, proven to be with all the data. So they succeeded, but there were nevertheless things that were learned in the process. So what's happening in California, and I assume that it's applicable in other climates that are similar, is we're moving to zero net energy buildings, and it's very soon, relatively speaking, in terms of the life of the building, there are code requirements coming up in 2020, 2025, and 2030 where all buildings will be required to be designed as natural ventilation, as zero net energy buildings, and natural ventilation is going to be a large component of that. These buildings and many others are documented in a publication. There have been 2 volumes so far, and there are 2 more coming out as we research very carefully all the buildings that are going up, and more every year there are additional zero net energy buildings to look at. It's mandated that these books were mandated by the Public Utilities Commission and sponsored by locally Pacific Gas and Electric Company, and you can get them on Amazon. As it turns out, it's a nonprofit publication, but nevertheless, it's available on Amazon. As I said, these are successful zero net energy buildings. Nevertheless, there are lessons learned that we want to look at, and we're a little focused on one kind of climate in California because most of the population centers in the state occur in this very common climate zone, the marine climate zone. It's generally dry and not humid, and there are some Central Valley. What we're doing is looking at the case studies in the Central Valley where it's very hot during the summer, and we're finding that the same methods can be applied, although it won't be over the entire year, which is the case in the marine climate. The thing about the marine climate is that temperatures are always in the range of the comfort zone, more or less, and on average, and we get fairly large daily swings of temperature, so it's generally cooler at night than it is during the day, and that's primarily because it's rather dry. But that's the setup that you see here, the San Francisco or Northern California climate, and then if you go south where it's warmer, it's not much different. It's a little hotter in the summertime, but it's a perfect setup for the use of natural ventilation for cooling. Now, in this, all the buildings so far that we've looked at adopted the same strategies. These 5 strategies are fundamental to making a zero net energy building. You reduce the energy use of the building so that you can minimize the size of the PV or solar photovoltaic system that's required. You can fit that solar photovoltaic system on the roof of the building or nearby on a canopy or something, and it matches the load, the energy used in the building, if you can get the load down to about half or 2/3 of what is normally done in practice. I'm broadly speaking here. And what I want to do is focus on the second strategy of natural ventilation on these 3 buildings that I selected because they use the same technique for each of the 3 in slightly different ways. So the first one is a building in the San Francisco Bay Area, which is used for training people actually in the electrician's trade. So it's a union type of project. And it is a zero energy building. Here's a floor plan. You can see it's fairly large with classrooms, meeting rooms, and office space. It's about 50,000 square feet. So it's a pretty big building. Originally, it is a renovation, which is interesting, and is tilt-up concrete panels. It had fixed windows, a solid roof, no skylights really, and uninsulated walls. It was built back in the 1970s when there wasn't an energy code in the state. So the natural ventilation design strategy is applied to this building, and as common to the other 2 case studies as well, is you provide bring air into the building from outside when it is good to use it for cooling. You can always bring in the fresh air, minimum requirement, etc. But you can use the outdoor air for cooling for most of the year. Then if you pre-cool a structure by night purging, night ventilation, you can cool the structure enough so that it takes care of the cooling requirement during the hot time of the year, which is not very much in the marine climate zone. So the combination of ventilation during the day during the swing seasons and during the winter and the combination of that with night purging during the few months where you would ordinarily require mechanical cooling combines to displace that cooling energy requirement. And they did this by retrofitting the fixed windows, and obviously you need to do that if you're going to naturally ventilate the building. And the windows are automatically operating and controlled by the central system. They had added roof monitors, which created with exhaust vents built in, so you could get a cross ventilation. When you have a big floor plate, it's important that you get ways to get the air to move through the intermediate rooms. They used air transfer ducts for that, and the designers had this distributed HVAC units for the mixed mode operation. I'll explain a little bit about that. So here is a picture of the retrofitted original fixed windows. They didn't put them in every single one, but periodically set in those windows. These are the roof monitors that had to be located for structural reasons in particular places, but they get daylight, and most importantly, they get those vents for the cross ventilation. And for the interior rooms, as I said, they have transfer ducts to get air flowing through to those rooms and then up and out through the monitors. And this is a typical interior room. A class is in session. So what's the lessons learned for this project? And this is very common for all three buildings, that the control systems we found, they each have communication protocols built into them, and they required a system integrator, actually a person who is very skilled at the controls programming, to integrate the programs, integrate the communication protocols to the central, to a central integrated control system. And in this case, the consultant decided to use a publicly available source. It was not a proprietary program, so this one is called Oppendium. And they had to, fortunately, because I guess they were electricians and they were smart enough to know that this was something they would run into. They had that consultant on board during the design phases, and then he continued during early occupancy to make sure the system worked right. So it turned out that they did this very well, but this was an important, and that the fundamental thing is that there is in the U.S. Until now, and that not available an integrated system of controls which is fundamental to making natural ventilation work as a system and tying into other systems like the lighting controls and so on. So that's one thing. The second thing is the kind of the mechanics of the room, that the actuators could only, as manufactured in the United States, they only could move to fixed positions, and they weren't continuously adjusting to the amount of air that was required by the system. So the result was a poor control of natural ventilation. And the third thing was actually kind of a disaster. In the classrooms, the actuators were so noisy when they operated, it would be very disruptive to the instruction that was going on. So what happened was they disabled the natural ventilation in those rooms, and so they didn't work. So the problem was really a hardware problem, but it was a lesson learned: is find a better actuator and make sure that they work continuously rather than just do fixed positions. The second one is a similar project. It was done in Silicon Valley, actually. It's a little bit warmer down there. It's similar floor plate, but this one is a much more open plan, and it was done as a speculative office building. So the developer has a very interesting story, which I will not go into, about how the zero net energy design was actually financially, he made more profit on the leasing of this building and leasing of this building, than he would have if he used conventional systems. It's a very interesting. I encourage you to read the book. It's explained in there very well. But I want to stick to natural ventilation for today's presentation. And here's a picture of the existing building. It was very similar to the first case study. It had fixed windows, it had a solid roof, and had uninsulated concrete walls. Now in this case, the designers decided, again, to use the same strategy. It's the same climate. So the idea is to have natural ventilation for the cooling and to pre-cool the structure through night ventilation because of large diurnal swings of temperature. And so, but in this case, they replaced, instead of the intermittent clerestories, they replaced the entire windows. And they also went for the electrochromic or dynamic glass, and I'll show you a picture in a minute if you don't know what that is. And they used especially designed skylights, and that was quite elaborate and is given in a more detailed space case study in the book. But it was openable skylights, so they essentially had the same kind of venting through the roof, and got some cross ventilation that way. But they did also insulate, the exterior walls and increase the exposed mass for the night purging. So it increased that performance aspect of natural ventilation, and was a very good idea. Of course, it had some costs associated with refitting the exterior wall. In the first case study, they did not insulate the walls. They decided, rightly or wrongly, that there would be no cost benefit to it, but these designers took the extra step of insulating the walls, and it performed extremely well as a result. And the last thing that was an addition in this case was the large slow-moving room fans to keep the air moving, and that makes people comfortable at a higher temperature, indoor temperature, and so you extend the range of the use of natural ventilation for cooling. So here are the windows. You can see the operators on the windows pushing out. The electrochromic glass, which electronically, if there is no sun hitting the window, it's a clear glass, and as sun hits it, it changes color due to the electronic nature. It's kind of a high-tech window solution. And given where it was, they wanted to use this solution. So that's the electrochromic glass and the operators and the cross ventilation. You can see it down low. And here is the skylights that were custom designed, very unique design. The skylights actually face south and so on. I won't get into it right now, but they had skylights which are operable, which let air escape exhaust from the cross ventilation. Here's the room fans that they installed. They are quite large and they're very slow moving. And then also a picture of the insulation. You can see it's quite thick that they added to the outside to improve the performance of the night ventilation. So the lessons learned, same thing. This client did not use the consultant who integrated the control systems. As I say, an integrated control system is not currently available in the US. So they had to program it and work with it. And that person was brought on board during working drawings, during construction documents and construction. And it took about 6 months to get the thing to work right. And in this case, they used a proprietary integration system. So the problem is that this natural ventilation system is made up of a kit of parts, and someone has to work on it, a good programming person, and stay with it to make sure that it works right. That's a drawback to what we have at the moment. The mechanical operators, again, had moved only to a number of fixed positions rather than continuously operating. I guess I only had 2 big lessons learned, but they were very similar to the first case. And the third building I want to talk about is actually a project that I was the project director when I worked for the firm that designed it. It's a library building in Berkeley, and it's a new building. And here it's only about 10,000 square feet, so it's a little bit easier to handle with in terms of getting air to the various spaces. There are some interior rooms. The issue here was that the street, it faces on a street that it was extremely noisy, and so there could be no openable windows. It was a library and had to be quiet. There were no openable windows that could be put in this facade, which is the south facade, and it was hemmed in on potentially in the future. There'll be a building on the left, and there is one now on the right, and so the only way to get air in and out of this building was in the back, one side, and the roof. So we have ventilating skylights, and we have air intake through the back into the spaces, and then some a unique idea, which is a wind chimney. When you can't get cross ventilation, you can devise a method, a strong method to draw the air through the building, and this has been used before, certainly in the Middle East over centuries. But the mechanical engineers suggested this as a possible solution, and that is what we come up with. And we have the mixed mode operation and a large room fans to increase the comfort zone, and just like in the other buildings. I'm sorry. And so this is the key about the wind chimney. We built it into the front of the building, since it's only a one-story building. And the air comes in through the north side. It's drawn through the building by the prevailing breeze is always from the same direction, right from the ocean side. And we're always going to get this kind of airflow during the day, or most of the year. We have this kind of airflow. And we didn't just theorize that the air would move that way. We actually tested it using software. And there is some, this was an early crude version of the software. It's about 5 years ago, I think. But it did show that this airflow would happen. And in this case, it was a different kind of interior shape, but it did show that it worked. And so we went forward with it, and then it's been built, it's been on operation for 3 or 4 years, and it does work apparently very well. The mixed mode of operation shows how we used the fresh air available through natural ventilation from the heating season in mode 1 all the way up to the peak cooling season. It has a radiant floor for providing the heat, piping warm air, which is generated by a heat pump. And the cooling side, because it's a heat pump, it can cool water can pipe through the slab, and for that peak cooling event, which right now, even now, still happens only a few days a year. Most of the time we live in a swing season. It's a good climate for that and for natural ventilation. So you get the air movement, the cooling is provided by air, and we also have backup fans, which if you look at mode 4, and there are poor conditions and the wind is not blowing for some reason, then there is backup low powered fans to help it. We did install some user-controlled operable windows in key places because I think there is a factor of the user feeling like they can have some local control, and their own requirements for comfort is important. So that was put in. It doesn't interfere with the overall natural ventilation system, but it's an important psychological thing to consider. So lessons learned were, again, it'll be repetitive, but this is sort of the worst case. There was no systems integrating person at the beginning, and there was no systems integrating person during construction, and it sort of evolved as a problem naturally, and it turned out that the control systems person was so intrigued by the problem that he spent a lot of time doing what was done by consultants in the previous 2 projects, and managed to program the various control systems into to a central system, and it was thanks to his dedication that particular issue was solved. So it was the same problem as in the other 2 buildings, and it was resolved, but it took a lot of work, and it's something that can be, it can't be using available products in the U.S. We're having all kinds of problems, and there is a solution which Yannick will talk about. Also, the window operators in this case again only had fixed positions. In fact, they started that they were all open or all closed. So this controls technician worked very hard to get it, but to get it right. But the first response of the owner was to raise the threshold of allowable CO2, and then the building felt very stuffy. So until this problem was solved of the control system, they were starting to get complaints from the staff about the building. And the other thing, if you look closely, you can see the actuators on the window, and you can see how large they are and so forth. That was the kind that was available 5 years ago and specified. We know a lot more today, and of course there are now other products. Again, Yannick will address it. So we had 3 buildings that were zero net energy. They did all the right things. They made natural ventilation a strategy, but the problems that all came up, the common problems that came up, they are solvable for these smart buildings. I'm going to use this as a transition and hand off to Yannick, because he's going to talk about how you can overcome these problems, really. So Yannick, it's all yours.
Thanks, Ed, for the presentation, and thanks for sharing this these very interesting projects. And now I will, move on to me and my part of the presentation. Hopefully you can see my screen now. And my presentation, I have titled it, Together we can create exceptional natural ventilation solutions for your building. And just moving on to the next slide here. So the agenda for my part of this presentation is a brief introduction on why we should have natural ventilation and how. And then a very brief introduction also about the design and which calculations you can do when you have a natural ventilation or mixed mode solution. And then moving on to the control systems, and last but not least, some of the case studies we have done recently. So first, why should we consider natural or mixed mode ventilation? That's one reason is, of course, we have seen that as a big part of it is, of course, the energy savings. There are different studies showing that we can actually achieve energy savings of around 80% compared to a complete mechanical ventilation solution. Besides that, we can also have a healthy environment. Actually, we can see that we can reduce, or natural ventilation can reduce the health saving cost up to 1.3%, and also reduce sick building syndrome symptoms with around 65% as stated here. Secondly, we can perform even better, and there has been some tests in classrooms where it actually shows that children where they have in classroom where they have openable windows could actually perform 7 to 8% better on different test scores. Also in offices, we can see that there has been stated a productivity gain of around 18% when you have natural or mixed mode solution. Also, you can also see that we can actually reduce the cost compared to a complete mechanical ventilation solution. Actually, we have seen that 8 case studies with natural or mixed mode actually can have a payback period of around 1 year when you combine all the different benefits like energy and product savings and etc. So there are quite a few, you can say, benefits having a natural or mixed mode solution. So when I talk about the natural ventilation, so that's actually based on you can say based on indoor air temperature, on CO2 level, on relative humidity, outdoor air temperature, wind speed, wind direction, and rain, etc. And of course, it is controlled using these actuators, which is shown on the second picture here, where my cursor is. And these are linked up to, it can be a dedicated control system This one is what we call InViComfort, but it can also be a BMS system where it's actually linked up to a BMS system. So actually, you can say we have a complete solution from the design. We can also supply the components, and we can also, you can say, have the control system for these kind of buildings. So speaking of natural ventilation, of course, that's one part of it. Another part of it is what we call mixed mode or hybrid ventilation. And that term is where we combine the natural with a mechanical ventilation solution, just to get that right. And one slide about WindowMaster and what we actually do. So we can say that we are actually in the complete building phase. So just right from the design of a building, where we can help sorting out which actuator should you use for different kind of windows. We can also help you with, for instance, do some energy simulations, some indoor climate simulations, etc. And we can also provide you with the actual solution of the natural ventilation. We can do the night cooling of the building, and we can do this solar screening, control that, and I will get back to that a little bit later. Furthermore, we can also do the implementations, for instance, the installation, the commissioning and testing, but also the handover and user training, which is also a very important part of it. Last but not least, we have also a service department, which of course can maintain the different system we have. So next one, next point is about the design and calculations. So of course, when you have a natural ventilated building, we can see that this size or this left picture here shows the overall system. So of course, you can see the very top building or the very top room here. We have what we call cross ventilation. The room down here we have single-sided ventilation, and down here in the atrium we have what we call stack ventilation. But if we zoom in a little bit on one of the room, we can see what is the essential part of a natural ventilation system is, of course, that we have openings to the outside. And these openings have we mounted, for instance, or integrated actuator which can open and close these windows depending on CO2 temperature or relative humidity set point, and these the temperature and CO2 and relative humidity is actually measured inside each of the room. Of course, we also have a keypad inside the room, so actually the people who are present can actually override the system. So if they want to open the windows even further, they can press open. If they want to close the windows, they can press close. Last but not least, we also have a weather station on the rooftop, measuring wind speed, wind velocity, but also, for instance, temperature. And all of this, based on all of these input, the weather situation, but also the temperature or CO2 inside the room, we can open and close the windows accordingly to that. So what we always say is that natural ventilation needs to be designed, engineered, but it also needs to be controlled. So we have, of course, seen many cases where it actually, when natural ventilation has not been thought of in the very early design phase, and that's also why the projects might not have been as good as intended, at least. So it's very important that the natural ventilation is designed. And of course, you can do various different kind of simulation or calculations. We normally do these basic calculations, in the very early design phase, but also the dynamic simulations is possible with natural ventilation, so you can say, or you can actually see what kind of indoor environment you can achieve throughout a whole year in different environments. Also, CFD is possible, and I will get back to that a little bit later. Of course, there are some requirements for instance, in US they have the Title 24, where it actually says that the natural ventilated spaces should have an openable area of at least 5%. So of course you can use this value as a startup value, but again, you need to consider, do we need more openings or and where and how should they be placed. For instance, so this is a building. So this is normally what we do in the very early design phase. So in blue is here, marked in blue, is actually the facade windows which we intend to use for the controlled natural ventilation. In green here we have a skylight. So you can actually see in this breakout room here, we can actually calculate, okay, how many air changes, so how much air can we bring into this room. So this is of course depending on the external wind speed shown here on the x-axis and the temperature difference between the inside and out. And based on this we can actually read, okay, how many air changes can we have inside this room. So this is a very powerful design phase tool that we can use in order to see if we should increase the number of windows or decrease them. Of course you need to be aware of the design of the openings. As you can see here, so normally when we have an openable window, we have an area here at the triangles, but we also have this area at the rectangular area, which you can consider as effective openable area. Of course, you need to consider also the surrounding buildings or the surrounding like this ledge here. So as you can see, when we open this window here, we only get the triangles as an effective openable area. So it's very important to take the surroundings into consideration as well. Also solar shading should be at least thought of. So here you see a picture showing the internal solar shading is actually fixed to the frame. So it means that we can actually open the windows without having the shading disrupting the airflow. Also down here, the second picture down here, we have external solar shading fixed on the frame, which means we can open these high-level windows without having any, you can say, issues with the solar shading. Second is of course this dynamic simulation. I will just briefly show you this one. So this is an office building located in the San Francisco area. So in blue is marked the automatic controlled natural ventilation openings. So it's actually every second window which we can open. We have the possibility to have cross ventilation in this particular building, and here is some you can say some input for this kind of building. For instance, we have to provide around 17 CFM per person in order to have a CO2 level below 1,000 parts per million. So if we press the run button, we can actually analyze how the indoor climate or the temperature would be throughout a whole year, starting from January to December. So in green is the outdoor temperature, and in blue is actually the indoor temperature. And of course you can see it's quite stable throughout the year, and when the external temperature is rising, the internal temperature is rising accordingly, of course, in this kind of building. And then of course you can say, okay, how much overheating do we have throughout a whole year? So for instance, if we look of the number of hours above 27 degrees Celsius corresponding to 80.6 Fahrenheit, you can say throughout a whole year in the occupied period we have around 25 hours. So it's not massive actually. So of course this model can also be improved even further. So for instance, we could have changed the glazing, we could have improved the solar shading, add heavy mass material inside the building, or we could actually also have more openable windows, and these results would of course have been better. But we can actually see that it is actually possible to have a really good temperature in an office building located in San Francisco. So going to the third here on my agenda is control systems. So what we have learned from its case studies is actually all linked to, you can say, control system, but also the hardware, meaning the window operator. So yeah, I just picked some bullet here from Ed's presentation. So window actuators are, you can say, are noisy, also visible, and the window operators are either fully opened or fully closed, which of course leads to a poor control of the natural ventilation. And it also mentioned that there's a lack of integration system designed actually to make the natural ventilation system perform perfectly. And these, of course, are something that I will address in the next couple of slides. But of course, the most important thing is, of course, that we should have the windows with either a surface-mounted actuator on, as you can see here, the very first image. We also have the possibility to actually integrate the actuator into the frame itself in many cases, so it cannot be seen from inside. Of course, we have facade windows actuators, but also skylight actuators, which is quite powerful, can also be used. And of course, we have different possibilities. So here you can see top hung windows up here. Here in this yellow building where we have parallel openable windows, it's also very used. Here is actually a hotel room where we have a side hung window. So there are multiple different categories and different windows. Of course, we can also, it's not only in new buildings, we can also do retrofit buildings. Here is a very old building in downtown Copenhagen. These windows up here are opened by our actuators, as you can see here on the very last image. So actually you can see we have surface mounted two actuators, one on the external window frame and one on the internal window frame, allowing the air actually to enter the space, to enter the office space behind it. So actually also retrofit buildings is a possibility. So here now I want to talk a little bit about the features or the technology we have built inside the actuators. So these are some of them. So inside the actuators we have what we call motor link features. So motor link features is of course where we actually can control the actuators millimeter by millimeter, and that is actually the pictures or the images showing this over here. So in many cases, actually, we don't have to open the windows fully. We can actually just open the windows to a very few degrees and allowing the air or enough air to enter the space. This is a very important feature for the natural ventilation system in order to make it work and in order not to be drafty also. Second, we also have incorporated 3-speed actuators. So this means that when the system is in automatic mode, it runs at a very slow speed, meaning that we actually have a decibel around 28, around that number. So it's very, very silent at least. The second speed is if the user then try to override the system, try to open the windows, then he will get, or he or she will get an audio feedback, meaning that we will run even faster speed on our actuators. Second, the third speed is if we have emergency situation, then we run at 100% speed. Then we also have the possibility to actually have multiple actuators on the same windows. As you can see here, we have two actuators mounted on the same windows, and these are interlinked with each other and have synchronization between them. So when the one actuator is moving, the other one is moving at the same speed also. Then we have the pressure safety function, which actually reduces the risk of entrapment when the actuator is closing. So if the actuators detect some resistance, then the actuator would stop. And we have several other features. So of course, all these features can either, for instance, be controlled by a BMS system or interlinked with a BMS system using one of these open bus communication protocols, KNX, BACnet, LUN, or Modbus. So this is one possibility. Another possibility is, of course, to use one of our, you can say, our control system, which we have two control systems. One is called NV Comfort and another one is called NV Advance. And these control system is actually very dedicated control system to control the natural ventilation actually. But it can also control mechanical ventilation, heating and cooling inside the building, lighting depending on the lux level inside and outside, solar shading again depending on, for instance, the lux level outside. And then of course we have the data logging showing what is, for instance, the temperature, what is the relative humidity inside the space, the CO2 levels, and also showing what set points the different systems are in. So these are are some systems that can be used in a building, also integrated, of course, to the BMS system if that's necessary. So the first one is our MV Comfort system. That's a touchscreen here, and that can actually control up to 8 zones, and that means 8 rooms. And of course, that is, as shown here, linked to our actuators, to our automated windows, and also linked to, for instance, the heating, the control. It can also be linked to the mechanical control, etc. And this is actually just this is the interface of the NV Comfort touch panel here. And here you can see actually that the room down here, Office 6, actually we control the natural ventilation, we control the fans, meaning mechanical ventilation. We also control the lighting, and we control also the heating inside the space. Yeah, going to the next one. So that's NV Advanced system, which can control quite many zones, an entire building actually. So this is actually the computer shown up here. With this computer we have a data exchange, or we have the possibility to have data exchange with, for instance, a BMS, another BMS system, if that's required. And then we also have the possibility to connect to this computer from one of our own service computers, and then we can see how the system is actually running. And again, we also have the possibility to connect to other kind of systems like mechanical ventilation, solar shading, lighting, heating, etc. inside the building. Yeah, touching on this one. So actually for the NV Advanced system we have, the openings is actually controlled by an external CFD simulations. So of course, for instance, when we have a high-rise building, we know that the pressure on the very top of the building is not the same as at low level. So for instance, the windows up here at the very top should, for instance, only open 10%, and the windows at the bottom should, for instance, open 50% in order to have the same amount of air entering the space behind it. Furthermore, we also need to take, doing these external CFD simulations, we also need to take the surroundings into account. So for instance, a building like this, here the first image is shown here, is actually shown with the wind direction from northeast. So in red here, we can see that we have overpressure on this facade. So this means that when we have a window here, we actually make all these readings from this CFD simulations and put them into our control systems. So this means that when we have a window here, we can see we have overpressure. So this means that when the wind direction is from northeast, the system knows that this window should only open 10%, for instance. When the wind direction then changes to southeast, we can see in here, the same window, we have a slightly under pressure, meaning, for instance, we should open this window 30% in order to get the same amount of air entering the room inside the building. So all of these pressure readings is then integrated into the NV Advanced control, and the control system then knows how much it should open and close the windows according to the wind direction and also according to the wind speed. So next and the last one is, of course, some of our case studies we have done. We have around 700 projects, or more than 700 projects around the world, which have either natural ventilation or hybrid ventilation solution. Of course, as you can see here, we have many different kind of building types. For instance, we have office building, dwellings, school buildings, also shopping center streets, actually, hotel rooms, and all of these is, of course, located around the world. But the first one I want to touch on is a very recent project we have here. Is with Harvard University. It's located at the Harvard Center for Green Buildings and Cities. And then you can see this building is actually a retrofit building utilizing 100% of natural ventilation. So there are no mechanical ventilation inside this building. if we go to this image below here, we can see we have high-level windows here with integrated actuator inside this profile here. And then we also have these skylights at the very top here, creating you can say a stack effect inside these rooms. So again, it's our EnviAdvance system which control the natural ventilation, of course, but besides that we also control the solar shading for this building and the heating and cooling integrated into the slab. And of course this is also very important that the natural ventilation and the heating and cooling is actually interlinked with each other, so they are not, you can say that the natural ventilation don't cool the building and you can say the heating is not on at the same time and so on. So it's very important that there is this interlink between all these different control system in the building. Secondly, we also have the PNC tower in Pittsburgh. This is a double skin facade. They also use here parallel openable windows. So what the air does is actually entering this double skin facade, as you can see here on the second image, and then throughout these grills here, the air enters the double skin facade cavity here and actually go down to this below these grills. And then on the inside we have on the third image we have these flaps open, which we can open, and then the air would actually enter the space in this meaning. And they have actually been seen that they can use natural ventilation for around 45% of the time. Another building which also uses these parallel windows is the Bullitt Center in Seattle. And actually you can see here that we actually push out these quite heavy large windows here on the facade, utilizing cross ventilation of the building. So it's also a very nice building here. Another one is actually the Baltimore School of Law. So they have a big atrium in the middle of the building, and in the facade they also have openable windows. So it means that the air enters these facade windows and then are being exhausted to this atrium. And they have found out that they can utilize natural ventilation for around 40% of the time in that particular case. Of course, we have also many other cases. These are just some of them, and we have many more on our homepage, which you can see. So going to the conclusion, one of the most important thing is, of course, that the natural ventilation design needs to be taken into consideration in the very early design phase. Of course, we have different possibilities to do calculations, but again, it's about getting the right design at the start. Secondly, we can also see that actually that natural ventilation system, if properly designed, are able to overcome the challenging points which Ed actually pointed out, and that actually means that we can have actuators which are invisible or at least also silence, and there are also products, actuators, which can be adjusted continuously, so not only meaning full opening and full closing, but you can also have our actuators which can actually provide these features. And third point here is, of course, another very important feature is that when you have a natural ventilation system, it's very important that these systems can be integrated to other systems, for instance the heating and cooling system, the solar shading system, etc., in order to get a very good and stable indoor climate inside. And of course, it is not only us, WindowMaster, who can handle this task. That's also why I wrote this last, that together we can create exceptional natural ventilation solution exact for your building. So of course this is a whole team effort. It's going from the very early design phase, from the architect to the engineers, but also involving, for instance, WindowMaster or other companies. So So I think this was my very end slide. Hopefully you have enjoyed it. We have now the Q&A session, and here you can also see there are some contact details for Edward Dean here. So if you want to give him a chat, you can do that. My information is here. And also, I have also written my colleague Esteban Sancho, who is the VP of Sales in US. His contact information are here. But I think now it's time for questions. So if you have any questions, now is the time to write these in the question box at the right side of you. So it says actually questions, and I will just open it right away to see if we have any questions online already. Just a second. Okay, we have a few. Okay, so yes, the first question is actually addressed to me. So that is which software do you use to make the CFD simulations? That's asked by Nicole. We have different possibilities, but the main, you can say the main software we actually use is a program called SolidWorks, which has this add-on feature for the CFD simulations as well. So yeah, so the answer is that we use SolidWorks for our CFD simulations, and that's both the external CFD simulations and external CFD simulations. And then we have Sarah has another question here. Are the actuators already integrated into the window products? And that is a yes and no answer. Thank you for that. The yes answer is that yes, it can be integrated into the you can say the window manufacturer. Perhaps already have a solution where they've integrated the actuator into their profiles. So for instance, Velux, the skylight manufacturer, does that already. But in many cases we can see that it is actually not the case. So so we actually need to come up with a design solution. So for instance, how should the actuators be positioned, and can it be integrated into the profile itself? So we have a team of specialized people which can look at, okay, how can we integrate the actuator into the window profile. So yes, sometimes the window products, or the window products are with an actuator, but in many cases the window manufacturer doesn't have this solution. Going forward, Sarah asked again, how about for hire? Okay, I'll just read it loud again. So Sarah has a follow-up question. How about for higher-end Windows systems, for instance, Schuko profiles? Yes, Schuko also have you can say, actuator, the possibility to buy a profile from them, which have an integrated actuator inside of that. It's not our brand, but so it doesn't necessarily have all the features which I just mentioned. But we also have the possibility to integrate our actuators into the Schuko profile, which we also have done in several projects. So yes, in high-end Windows systems might have the possibility, but in some cases they don't. Let's see here. Okay, I see. Thank you, Sarah says. And then we have another question. Does your BMS uses PID parameters or just PI? So yeah, that's actually that question leads on to another webinar we also have. But it can be actually it can be both of them. So depending on what we actually controls inside the building, we have different control possibility, either to have it done by the PI, quite simple, or actually also to have the PID, yeah, as a possibility. but perhaps yeah, we can have a chat about that a little bit later, because that's actually another whole session. But actually our system uses both, depending on what we actually control in the building. So I also have a question here that's actually not for me, that's for Ed. I think we can still have, even though we are on time now, I think we just take a few more questions here. So this one is for Ed. So just reading it loud here. It says the case studies you have shown is oh, sorry, there it was again. Yeah, the case studies you have shown is mainly with those with are not functioning right. Are there any of the cases in your book that actually also have a good or a perfect natural ventilation system?
Well, first of all, let me just say that they are all functioning correctly, but it took some work and an understanding of the programming necessary, and either a special person on board from the beginning or it came in after, which was harder to adjust the systems. But they all ended up working fine. The real point was that they were not aware of, or it was not available even, to use a fully integrated system, as Yannick just described, that is now available, and all of that headache could have been avoided if we had then what we have now, the possibility to use. There were over 20 case studies, and I cannot think of one yet that utilizes a system as integrated and straightforward as the WindowMaster system. So it's one of the reasons that I personally am very interested in seeing it applied in zero net energy buildings as we go forward and build more of them.
Okay.
I hope that was a good answer.
Yeah, it was a very good answer. At least I thought so. So I think we have another one for you, Ed. So you mentioned the books. Where can those be bought? Does it say? Where?
The best. Yeah, the best place right now is on Amazon, and if you if you type in on the Amazon website under books, zero net energy buildings or zero net energy case study buildings, they'll come up there. And there's 2 there now, and in a few months there'll be 4, including one on residential projects.
Okay, perfect. I think we'll take the last question here, and that's from Enrico. Just read it loud here. Have you ever evaluated the ventilation of old massive buildings in hot plus humid and cold plus humid climates?
This is for me, or?
It can be for you and for me. So have you done that, Ed?
No, it's not humid. It's not humid in California, so I haven't had the chance to do that. It would be wonderful to look at such a building.
Yeah, actually we have done some, you can say, evaluation of that, and in some cases you can say that you can have some material which can absorb to some extent the humidity, but again you need to think about the building as one. So of course in these hot and humid climates, sometimes it's not a possibility to have the natural ventilation solution during the daytime. Perhaps you can use it during the nighttime, or you can use it during another part of the year where it's not hot and humid. But I think if you Google hot and humid climate plus natural ventilation, I think there should be a report on that as far as I remember. Okay, just see if there are quite a few questions still waiting. I'm not sure if we have the time. We are going 5 minutes above the actual time. I think we'd take the last one, the very, very last one. That's from Nicole here writing that, do you simulate the whole building or just part of it when you do the internal CFD simulation? Yeah, so actually we, depending on how precise it's going to be, but normally we would just take one room and do the internal CFD simulation for that particular room. Yeah, where we do, you can say, where we have like a wind tunnel, yeah, built up inside our CFD simulation software tool. But of course, a possibility is also to have the full model inside the software and do that as well. Yeah, I think that was the last question due to the time limit here. But thank you very much for listening in to this, and thank you, Ed, for participating and giving us a very interesting presentation also. And if you have any further questions, you are more than welcome to contact one of us. You have the contact information here, and also we can send you the slide. Yeah, the slides show the slides which we have actually done here. We can send them to you by mail, and also in a couple of days, hopefully this recorded webinar would also be available on different on our homepage and different other places. But thank you for listening in, and thank you, Ed, for participating. Very interesting as well. Okay, thank you very much, and have a nice day, and hopefully see you at our next webinar. Bye bye.